Good evening, everyone.
Hello.
All right. Who wants to start us off? Susan, do you have a question?
Yes, I do. Would you mind looking or talking about number 4.26, question B?
Absolutely. Yeah, these get a little tricky, and once you see, some of it, you'll be like, oh, they're just trying to mess with me.
Well, they succeeded.
Yes. So the first thing I suggest is doing like a coloring like I've done so that you can visually see where all these things are, right? Because when they ask for this first part, which is what's the probability of A happening given that B has already happened? Well, if B has happened, that means we're living in the green zone, and only these three green things are kind of like our whole new total. And amongst those green things, are any of them blue things? And the only one is the 0.22. So that's the only intersection. So that becomes our good, is 0.22. And then when you put them all together, 0.36 is your total. So you get 0.22 over 0.36, and that becomes your probability.
The second one I had a lot of trouble with, the one right after that.
Yes, and everybody struggles with this one because the answer is impossible. The answer is 0, and it throws everybody off because we're given that we don't have B, right? The little line over it means the complement of B. So basically, we're given that we're living with a sample that comprises of everything but the green stuff. So we have these three columns. And then the question is, given that we're among those three columns, what's the probability that we get an event from B over here? Impossible, because there's no intersection. So that's a probability of 0.
Oh. Okay.
And that's why it's a probability of 0, because there's no overlap, right? You can't be in the complement of B and in B at the same time because they're polar opposites.
It's like being there and not there. Okay.
Exactly. So the last one says, okay, now we're given that we're living in C. So we're only living in the yellow stuff.
Right.
And if we're in the yellow stuff, what's the probability that we get something that isn't in B? Well, B is the green stuff. Right? So everything that's not in B is everything outside of it. And so basically only looking at the yellow stuff, right? How much of the yellow stuff isn't in B? And it's all of it.
Oh, because I was trying to figure out how you choose which of those 4 were the values.
You get all of them because
you get all of them. Okay.
Because remember, the good is everything that satisfies the question, and everything in this, kind of new set of data, because we're only looking at the yellow stuff. Everything in this new set satisfies the condition of not being in B, and because it does, then we're good to go.
So it'd be 0.14 over 0.14.
Yeah, which would equal 1.
Which would equal 1. Okay, right. Okay. No, that's not what I came up with, but all right.
Yeah.
Makes more sense.
Those are tricky. And especially because, they come out to be 0 and 1. So those always make students' heads explode.
Thank you.
Yep. Who's next?
If we could do part C of that same problem.
Sure.
Thank you.
So A union B means everything that's in A or B put together, right? So A union B just means all of the blue and all the green put together. So all you have to do is add all those things up. Make sure you don't add 0.22 twice, right? So it's 0.1 plus 0.15 plus 0.16 plus 0.22 plus 0.10 and plus 0.04. You add all that, and that's your good. And then you would divide by the total, but the total is just 1, right? If you add everything up, it adds up to 1. So it's basically just these things, divided by 1. So it just becomes those things. The intersection of something is just that. You look for the intersection. So we're looking at where A and C cross, right? So we're looking for where the blue and the yellow intersect. Well, what do we notice about blue and yellow?
They don't intersect.
Exactly.
Well,
So their intersection
zero?
doesn't exist. So that's a probability of 0. Yep.
Mm.
And then we do the same thing. Sorry?
The last one? Is that
Yeah.
the same thing for the last one?
Well, let's see. B intersects C. Well, B is green, and yeah, because there's no intersection between those as well. So
No.
that probability is 0 as well.
So both of those was 0?
The last two, yeah.
I don't understand how we.
Well, probability is basically saying if we pick one person at random, what's the probability that they have a given characteristic? And in the case of these questions, they say, if I pick somebody at random, what's the probability that they have characteristic A and characteristic C? Because that's what intersection means. It means you have to have both, right? It's A and C. Well, characteristic A is the employee works at the high capacity level. Characteristic C says the employee has little or no formal training and works below high capacity. Well, how could they be both of those same things at the same time? They can't. It's impossible. And if you look at the table, you look at the colors, right? The yellow represents the ones that have little or no training and work below high capacity. They're in the low and medium capacity and they have little or no training. So that's just those 4 categories there. And if you want to think about it rather than percentages or these decimals, if there were 100 people, 100 employees, you would have 1 employee who had no training and worked in low capacity, 2 employees that had little training and worked in low capacity, 5 that worked in medium capacity with no training, and 6 that worked in medium capacity with little training. And those 11, 12, 13, those 14 employees are the only employees that satisfy condition C. And then you've got all the other employees down here on the bottom row that satisfy condition A, because condition A is just simply they work at the high capacity level. So it's just those 4 groups that work at the high capacity level. Well, this is asking the question, what's the probability that if you pick an employee at random, they're going to be both an employee who works at high capacity level and, because intersection means and, an employee that has little or no formal training and works below high capacity. And that's impossible. There's no intersection between those 2 things. So that's why that's a 0. Things can have probabilities of 0. Anything that's impossible has a probability of 0, like me dating a supermodel. That's just not going to happen. For one thing, it would piss my wife off to no end. Right? So there are plenty of things in the world that have a probability of 0. There are plenty of things in the world that have a probability of 1. So don't be thrown off and think that something is wrong because you're getting an answer of 1 or 0. 1 and 0 are both completely legitimate probabilities. The only answers that would tell you right off the bat that you've screwed something up are numbers smaller than 0, i.e. negatives, or bigger than 1, because those are impossible, right? All probabilities are between 0 and 1. Anything else, you've messed up something. Okay, so does that clear it up for part C?
Yes, thank you.
Of course. All right, anything else, guys? Are we good with the rest of these? I know we need to go over 51 for sure, but is there anything else before we get to 51 you guys want to discuss?
maybe 46B.
Okay. So 46 is a binomial, and we recognize it as a binomial because we have a set number of trials, right? We have a random sample of 20 products. So there are certain conditions that we have to have in order to recognize or know that we have a binomial. The first being that we have a set number of trials, and they talk about N as in Nancy being the number of trials. And in this case, N equals 20. In addition to that, you have to have that your trials, each one of your trials, can result in either a success or a failure and no third option, right? There's two options, either a success or a failure. But really anything in the entire world can be placed into two camps, because whatever you categorize as a success, just all other options become a failure. So really that rule kind of becomes a no-duh rule, because any situation can be forced into a binary situation where you have a success and a failure, and you can have multiple things that count as a success and multiple things that count as a failure, or one of each, or one of one and multiples of the other. Doesn't matter, just as long as you define something in such a way that there's a clear-cut success and a clear-cut failure. And all of these
What did you,
sorry?
what was that you said about N again? N is what?
N is always your set number of trials. The set number of times you're going to repeat the experiment. And in this case, they sampled 20 return products, i.e. they picked a random return product 20 times, meaning they repeated the experiment of grabbing a random product 20 times. So that's their number of trials. They had 20 trials, i.e. the 20 products that they chose.
Okay.
If you went out and asked 35 people a yes/no question, then N would be 35, because that's how many times you repeated the trial of going up to a person and asking them the question, recording their answer, go up to another person, ask a question, record their answer, right? That each one of those is an experiment. Each one of those is considered a trial. And N is just the number of times that you repeated that thing. So in this case, N is 20. So we have to have a set number of trials. We have to have that it only has, binary responses. There's only two responses or two groups of responses, right? You either have something that's considered a success, something that's considered a failure, and we can always define both the success and the failure to have multiple options that classify as that. In addition to that, there has to be a set probability of a success and a set probability of a failure. And those two things have to add up to one, right? Because they have to be complements of each other. So if there's a 35% chance of a success, there has to be a 65% chance of a failure. And those probabilities must remain constant. They must not change from one trial to the next, right? So every single time you go out and ask somebody that yes/no question, there must be the exact same probability of getting the yes answer as there is each time. And you might go, well, how is that possible? Because everybody's going to choose to answer yes or no differently. The idea of that having a set probability is the fact that somewhere in the past, people have studied that same yes/no question or a similar yes/no question, and they know on average what percentage of the people would say yes. So if on average 20% of the people would say yes, then that means the probability of each one of your random people saying yes is considered to be 20%. So that's how it works in that situation. And it's kind of similar the way they set up the context of this question, because they tell you, each of these defects have a known percentage distribution from previous samplings, from looking at previous defective products coming through this control department or whatever. they know that in the past, 5% of all returns are defective and can't be repaired. They know that 45% are defective but can be repaired. They know that 35% have small surface scratches but are functioning perfectly. So they're basically, the scratch and dent kind of thing. So there's nothing wrong with them functionally. It's just cosmetic damage. And then 15% of their returns have nothing wrong with them at all. People just return them because, they changed their mind, or they just, whatever, didn't want the product. And those percentages are set in stone. Now, that doesn't mean that if you went and randomly grabbed a set of returns, you're always going to get this exact distribution of problems. It just means that you have a large enough sample from the past that this is what you would see on average. And so you would expect to see something similar to that in any other sample you took. It's not going to be perfect, but it should be, similar. But anyways, in order to do a binomial, you assume basically those things to be constants, because you have to have that for a binomial. So you have to have a set number of trials, and you have to have basically a set constant probability of a success and failure. And you have to have, only two possible outcomes, success and failure. And that's really all you need in order for something to qualify as a binomial. So you can see that it's pretty easy to kind of force a square peg into that round hole, because those aren't a lot of rules. And those are rules that are pretty easy to kind of, I wouldn't say bend, but make your stuff fit those rules. So it's really easy to apply a binomial to most scenarios out there. So that's why it's widely studied, because it's widely applicable. Okay. So for part B, if they want exactly 6 of the 20 returned products to be defective and not repairable, well, it all comes down to just understanding what are all the bits and pieces, from the given information, so that we can set up our binomial. So for instance, we need to know n. Come on, write for me. Try that again. N. That's a terrible n. We need to know n. We need to know p, which is the probability of a success. And then we need to know x, which is the number of successes. And those are the only 3 things we need to know in order to compute a binomial. Well, n is easy, because for all of these questions, n is 20. That doesn't change, because we're always just grabbing 20 things, right? We're always looking at basically a random sample of 20 things. Now for B, what's x going to be for question B?
Six.
X is gonna be 6.
Very good. Yep, very good, both of you. X is 6. Now, the last thing we have to figure out is what P is. Well, we have to look at the description. We're looking for products that are defective and not repairable. According to the descriptions up here, what percentage of things are defective and not repairable?
Well, it would be 50. No, it would be 5%.
5%, very good, right? Because it's defective and not repairable. So 0.05. Then all you got to do is stick those 3 numbers into technology, whether you do it in a graphing calculator, whether you do it in Excel, or whether you do it in SAS. It's easy, because you now have all the bits and pieces, right? So if we want to do it in SAS, we're doing a binomial. And are we doing a PDF or a CDF for that question?
PDF.
Yes, we're doing the PDF, because we want to know exactly, not a equal to or less than. So we want to do a PDF.
PDF is for exactly. I struggled with this yesterday.
Yes, a PDF is precise, right? P for precise. So a PDF means precisely this many things. And then a CDF is a cumulative thing for C, and it adds up the probability of getting 0, 1, 2, 3, 4, all the way up to whatever your X is. So in this case, our X is 6, our N is 20, and our P is 0.05. So we'd want to highlight that and run that. And that would be our answer for that one. And it's just that simple. And if we wanted to do, the first one, all of the 20 return products have some type of problem. Well, N is still 20. X now is 20, right? Because all of them are a problem. So X is 20. And we just have to figure out what the probability is, right? So, well, what does it mean to have some type of problem? Well, isn't that going to be everything except for the 15% that have no problems? So part 1, our P is just going to be 85%. And our X is going to be 20. That's one thing that's going to differ, right? So in our technology, all we have to do is change X to be 20 and this to be 85. And then you run that one. That's the answer for that one. Okay.
Dr. McBride, is the I used SAS for parts B and C, but for parts A and D, since they were all the same, I used the dash method. Is that appropriate or not for these types? Because I just figured 0.85 to the 20th is just quick and easy to put into my calculator.
Absolutely. I love you. Yes, the dash technique works beautifully for both A and D. Absolutely. That's fantastic.
Thank you.
That's great.
Yay! So glad.
Yes, very good. Very good for all of you who thought of that. Fantastic. Give yourselves a gold star because that's fantastic. It's always good to be able to kind of think of the more lean, efficient way of doing it. That's fantastic. Yes. So the only other one that we would have to do in technology would be C. And it's 6 or more are defective and not functioning properly, right? So again, we know N is 20. Now we have X is 6 plus, right? 6 or more. And then the probability of defective and not functioning. So that's where it becomes tricky because what does that mean to be defective and not functioning properly? That's where I don't like this question because the wording makes it a little too easy to interpret different ways. I personally interpret it as if it's defective and not functioning properly, then it's these and these, because these are both described as being defective. Just because one is repairable and the other is not, doesn't change the fact that they are defective and not functioning properly, right? Those are both of those categories are things that are defective and not functioning properly, some of which can be repaired, some of which can't. These 35% are definitely not defective because they are functioning properly, right? It says not functioning properly. So those don't classify as that. And then of course, these don't classify as that because they have no problems whatsoever. So in the case of C, your probability should be 0.5. Now, because we want 6 and above, right? We want 6, 7, 8, 9, we want all of these. The only way to get this is to do a CDF and subtract, because remember, a CDF goes from 0 up to something. And obviously, if we want 6 and above, we need to subtract the rest, which means we need to stop at 5. So what happens is in our technology, we have to use X of 5 and do a CDF. And then we have to do 1 minus it, because if we do a CDF with 5, it's going to give us this stuff when we do the CDF of 5. And when we subtract that from 1, it will give us the leftovers, which is 6 through 20, which is what we want. So that's how you tackle that one. Questions on any of this? right, then let's move on to the real tough one, 51. That's the one that gives people the most problems. And again, part of it is it just doesn't explain things well. Like part A doesn't say anything to indicate that they want you to do part A as a binomial experiment. I guess you can kind of infer it from the description, right? That you have a set number of trials, i.e. 2,500 hits. You have a constant probability of a success being 1 out of 1,000. And they tell you how many successes they want, right? So it fits a binomial where n, a number of trials, n is going to be 2,500. My probability of a success is 1 out of 1,000, right? Which is 0.0001. And for part A, we'll have no more than 5. So no more than 5 means X is 0, 1, 2, 3, 4, and 5, right? That's what it means to be no more than 5, is we can have up to and including 5 sales in a randomly selected day. Well, if we want 0 through something, is that going to be a PDF or a CDF?
So would there be a CDF?
It would, very well. Good job. Yes. So we would go back to our technology, whatever technology you want to use. We would change our N to 2,500. We would change our P. Oh, we don't want to do this one. We want to do a CDF. 2,500. We would change our P to 0.0001. That's 1 out of 1,000.
That's one too many zeros.
Is it?
0.001. Yeah.
Oh, that's right. 10, 100,000. Thank you. And then our X was up to and including 5, which is what we got right there. So now we just highlight this and we run that. And there's our probability of something is.
Dr. McBride,
Yes.
when I was looking at that, the problem I was having is I was reading it as more than 5 rather than up to 5.
Yeah.
You have to do the 1 minus.
Yeah, you might. We'll have. Oh, I'm sorry. We'll have more than 5. For some reason, my brain, I had we'll have no more than 5. Oh God, I put a no in there. Yes, you're absolutely right. So we would have to do 1 minus that number. Yeah, very good. Thank you.
1 minus
I
that
don't know
number. Okay.
why I had that brain fart and thought it was no more than 5, but yes, more than 5. So yes, very good. So we would have to take this number, right, and subtract that from 1 to get the actual answer.
Okay, subtract from 1. Okay.
And then part B says, you know, what do we have to assume in order for this to work? Well, remember, we have to have a set number of trials. We have to have a constant probability. And so we need to basically explain that in the context of the question. So that just means that we have to assume that the internet hits are independent, because that's one other thing that we have to have. Each trial is independent. I forgot to mention that. And then the probability of a sale has to remain constant, right? So every day, this probability of being 1 out of 1,000 doesn't change. Those are the conditions of the binomial in the context of the question. That's all that we're doing there. Okay, if we want to do the Poisson approximation, we have to calculate a couple things. We need to know mu, or the mean, which is always just n times p. So the mean of a binomial is simply just the number of trials times the probability of a success, because that makes sense, right? If we win a game 30% of the time, if we played that game 10 times, we would expect to have 3 wins, right? 30% of 10. So we just get the number of trials times the probability. So in this case, 2,500, right, times 0.001, and we get 2.5. 2.5 sales per day is their average. And that's all you need to know for the Poisson, right? The Poisson just uses the
I have
mean.
I have a really random question.
Sure.
Why do they call it the poisson, since that is French for fish? I was
I'm
just wondering why they
assuming,
call it that.
I'm assuming that the French mathematician who came up with it, his last name was Poisson.
Oh, okay.
That's usually what it is. Most of these things are
Yeah.
named after the egomaniacal people who thought them up.
That makes sense. Okay.
Yeah, I always wondered why it was named after a fish as well, but I'm pretty sure it was after some dude with that last name. Okay, so we want compute probability the firm will have more than 5. So it's the same thing that we want more than 5. So we have to do a PDF up to 5 and do 1 minus it, right? Because it's the same, basically the same question, only now we're just calculating it differently. So we have to do the PDF Poisson, and yeah, PDF, P as in Paul, right? And in this case, our X is 5, and our M is our mean is 2.5. And if we run this, we get that. That seems wrong.
It's the CDF.
Oh, I did do the PDF, didn't I? Gosh darn it. What is wrong with me today? Thank you. There we go. That looks better, because that number should have been pretty close to our last number. And of course, if we subtract that from 1, we're going to get 2 answers that are very, very close to each other, which now tells you what the answer is to the last thing, which is it accurate? Absolutely. They're very similar. And the reason why it's accurate is because they're very similar in what they do. We talked about this early in the week. Oh, look at that. Named after Dennis Poisson. Thank you. Yep.
I had to look it up since
Yeah.
I was, yeah.
Yep, that's what it is. It's all of those things. The Gaussian rule was named after Gauss. The Cartesian plane was named after Descartes. I mean, they're all a bunch of egomaniacal people. So because the binomial and the Poisson are so similar in what they measure, it would make sense that we would get a similar response, right? The only difference between a binomial and the other is the binomial is X number of successes out of X number of trials, whereas the Poisson says X number of successes given an average number of successes, which basically comes from number of successes over a certain amount of time rather than a certain number of trials. But you could see that if we have 25 hits per day and we're asking that this happens each day, then that expanse of time is really the exact same thing as a number of trials, because one day just equals 2,500 trials, right? So that's why you're going to get roughly the same answer from both of them, because they're basically computing the same thing. They're asking the same question with a slightly different context. Okay, anything else?
So I haven't had a chance to. I just tried to pull it up on the homework set. I'm trying to pull up the project, and I'm having trouble finding it.
The mini project?
The big project, the
Big
final
project.
project.
I was going to say, because we already did.
Is that not on Google?
Yeah, it should be.
I don't know. Is anyone else having trouble finding it on Google? I wasn't able to even find that the little cheat sheet that you had on there yesterday. I wasn't able to see that on there.
cheat sheet. Oh, you mean the SAS how-to?
Yeah, I wasn't able to find that. And
That's, that's in the SAS folder, right? So you go to, I'll show you.
is the final project in there too?
It might not be because the final project is just explained in the course, in the assignments. So,
Okay, so that's the only place that it will be.
yeah, if you
So I,
go
okay.
to SAS stuff. this is
Yeah, so
where-
I saw it right here. I just thought that it's because it's pulling up weird on my computer. Like it's not, I'm trying to download it from that place, and then so I thought maybe it was on the Google
Well,
Drive.
the data sets are there if that's what you're asking, but the actual like syntax questions are not anywhere. Like I didn't put a Word document with all of the questions like I did for all the homeworks, right? So there's not a version of this for either the mini project or the final project.
Okay, yeah, that's what I was asking.
Yeah, but the data sets are there.
Okay, got it.
The final project is just, you know, if you go under assignments, it's all described within that assignment. So if you go to the final project, everything you need to know and need to do is all described right here, right? If you open this document, that will have everything you need to do in that document right here.
Okay.
And I guess I should save it to the Google Drive. I don't know why I never did, but it's there. Okay, what else?
I had a question. If we submitted our homework to you early on Tuesday, you haven't replied to any of that yet, have you?
No, I haven't got around to doing it. I probably won't do it till tomorrow when I have them all at once.
Okay. No problem.
Yep. Anything else?
I have a question. Another, I'm sorry. So, I was watching this video from you, and it said that something had to be turned in on Turnitin, and I was confused. It was another class, but
for us, the only thing that gets turned in to Turnitin is your critique.
critique. So do I have to submit it there too?
If you submit it through Turnitin, it gets submitted to the critique automatically.
So I just submitted mine under that post.
Right, you have to post it, but then you also have to take the Word document and submit it to Turnitin. If you click on the Turnitin.
And then just upload the assignment?
Yeah, exactly.
Oh, okay. So
in student view, it'll just have a little start assignment, right? You click on that and then upload file and you choose your file wherever it is on your, no, the critique is due as a posting to the discussion board today. You technically have until Sunday to turn it in, but I mean, if you've written it all up and posted it, then it should be done. So you should be able to submit it.
okay.
So, I mean, technically, yes, it's due today because you have to have it finished in order to post it to the discussion board.
Okay.
Okay, what else?
Dr. McDonald, I had a question on that same assignment. I mean, I know we're supposed to submit to turn in. I mean, what kind of score are you what kind of score do we need to kind of, if you get a certain type of score, is that unacceptable?
It should be green, which I think green is like less than or greater than 75%. I think they do it as what percentage is original? I think
Less than 26%.
yeah, something exactly.
Yeah, that's 26. Yes, that's.
So you
Okay.
can't have more than 26% in common with other sources, basically. So
Is that after you exclude? Because I have like 8% after I exclude my sources, but it's like yellow with the sources.
yeah, absolutely.
Yeah, I had the same thing. So
Same
Yeah.
thing, yep. Okay.
Yeah, by sources you mean your
The bibliography.
bibliography. Yeah,
so
absolutely.
and I had to put my variable names in a quotation because otherwise my variable names show up as in another document. And they were the variable names used in the study. So then I excluded quotes.
Oh, sure.
I don't know if that's okay.
Yeah. I
Okay.
really I only go and look at ones that have really, bad scores. If it's borderline, it's usually because of things like that. But if they're really bad, then I'll go in and look at them and go, wait a minute, I had a student that just copied a lot of the research article without putting it in quotations and citing it. And so it came back with a really bad score. And I just said, hey, you gotta cite this properly. And so it's things like that. Anything else? All right. Well, one of your classmates had a really interesting paper that I wanted to point out some things in it. And I probably should have figured out where it was posted so you could get their synopsis and stuff like that. But the bottom line was they were doing some interesting things in this paper, but they were also not explaining things well enough, right? So it's a good example, in my opinion, of I think they're doing some good work. I think they could have done a much better job of explaining what they were doing. And this is something you want to think about when you're doing your dissertations. The rule of thumb is you should explain your research thoroughly enough that somebody else could replicate it and get the same results. So that means you have to describe, your sample, how you got your sample, where your sample came from, and then all the data that you got from the sample, how that was attained. Then you have to describe precisely how you analyzed all of your data or manipulated it, right? In the case of this, they basically just asked employees a bunch of survey questions. And then from those survey questions, they created what are called scale scores. So for instance, the enjoyment of gaming was measured with a 4-item scale. And what that means is they just took 4 of the survey questions and lumped them together and considered them as a family of questions that all, quote unquote, measured the same thing, i.e. the enjoyment of gaming. And that becomes a scale score. And they did this over and over again, right? So recognition had a 3-item scale score, and usefulness of gaming had a 5-item scale score. And I didn't look thoroughly. Maybe it's in the appendix or something at the end. No, it doesn't look like it. Nowhere do they actually give you the survey questions. Nowhere do they give you the survey questions that go into the scales. I mean, they give you a couple examples, but they don't give you all of them. So for instance, right, in this 4-item scale, they give me one example of I find the experience of the Bravo system enjoyable. Okay, great, but where are the other 3? They give me this alpha score. Well, what the hell does that mean? Right? I think it probably means that they did an internal validity test, which basically asks how well are these 4 items actually related. And this was the score for that, I think. But I don't know, because alpha can mean a lot of different things, right? So there would be a lot of questions if I was reading this as, you know, somebody who was going to say whether or not this would get published. But they, you know, they did some interesting work and they got some interesting results. So, you know, like here, again, they list all of these numbers. It's like, what the heck do all these mean? You really have to read through it. They just didn't do a good job of describing everything. So keep this in mind when you're, obviously you don't have to worry about that for this class. You're not doing anything like this with your final project. But when it comes time to do your dissertation, just keep in mind that you've got to explain the crap out of everything, right? You really, really want to be thorough and explain everything. Okay. That's
It would
it.
be nice
Okay.
to see those questions, because like, how do they,
Yeah.
how do they define enjoyment and usefulness?
Right.
It can have 1,000 different definitions.
Yeah, exactly. Yeah, that was my point. I thought so too. It's a wonderful study. I think what they're trying to get at was really cool. Gamification is a very popular thing right now, which is probably why it got published, because the publisher thought, ooh, gamification, everybody loves gamification. They'll definitely read this. You know, and they got dazzled by all of these lovely tables of results. But I would have read this as a reviewer and said, no way in hell I'm publishing this, because there's not nearly enough information for the reader to really be able to believe it. I mean, sure, if I just take their results on face value, okay, great. Then they tell me that this thing works and gamification had a statistically significant impact. But I don't see any actual proof of that. I just have to take their word for it, and I don't like that. And you shouldn't either, right? I mean, that's one of the things as being a good consumer of statistics, is that you need to be a skeptic and you don't believe things until they give you enough information that you go, okay, now I know it's true because they told me how they got their data. They told me where the data came from. They showed me how they analyzed it. So now I know that these results are legitimate. If they're just giving you the results without showing you what's underneath the hood, you're like, well, how the hell did you get from point A to point Z? All right. That's all I got for you guys. If you got no more questions, we can get out of here early.
Thank you, Dr. McBride.
Thanks, Dr. McBride.
Of course.
Thank you.
Yep. My pleasure.
Thank you, Dr. McBride.
Good night, everyone.
Good night.
Bye.
Thank you.